Hello, and in this video I'm going to introduce you to repeated measures ANOVA, the one-way repeated measures ANOVA, and particularly really focus on the pragmatics of what it actually means and how to do it in R rather than the mathematics behind it, because some of the ways you can do it in R, that gets quite complicated. And indeed, even in this easy way that we're going to do it, the process itself is a little different than some other analyses we've done in R. So we're definitely going to focus on the pragmatics. So what is a one-way repeated measure ANOVA? Well, this is a bit different to all the other kind of between group analyses we've done, because a repeated measure ANOVA is where you measure people repeatedly on some variable. So you get them to do one condition, and then they also do another condition. There might be some counterbalancing, changing the order that people do different conditions depending on who they are, but you don't have separate groups of individual people who you subject to the different conditions. Everyone does all conditions. That has some practical advantages and some statistical advantages. In one sense, it has practical advantages because it's easier to recruit participants, get more participants, and it's more sort of economic of financially that way. It has some statistical benefits if you think about it, because if we're getting the same people to do our different conditions, all that's theoretically changing is that the task that they're doing. If we don't use different people, theoretically there's no variability introduced by individual differences. There's always some error, but in theory, that's the theory of repeated measures ANOVA. We should have no individual differences between people, because people are doing our different conditions. So from that, it seems like quite a good technique, but it does have certain issues. One is, if we know that our scores are going to be related or correlated to some degree because they come from the same people, we have to know how much, so we can take account of that in terms of our analysis. But basically, what the repeated measures ANOVA assumes is that relationship, or the covariance between each of the conditions that people do is the same, because if it's different for different conditions, that's a confounding factor, and we can't say what is due to the experimental effect and what's due to the differing variability. So that's kind of the theory of repeated measures. We're going to have several different conditions. We're going to have the same people measured under the different conditions. I normally don't spend so much time going over theory with you, just staring at a blank screen, but I wanted to go over that today because it's the first within subjects or repeated measures ANOVA we've done. The other ones, the one-way independent ANOVA, the two-way ANOVA, and obviously the simple effects analysis have all been done on between groups of different people who were randomly assigned to conditions. So I just wanted to explain some of the theory of it. Anyway, let's dive into our example. So I've got R open down here. If we open R, we see that our example data for this video is contained in a data frame DEP, and what this is we've tested 12 participants, and they're all tested in all the different conditions. Here we've got 3 groups: pre, post, and follow up. The idea of this fictitious study was we were wanting to test a treatment for depressed individuals, and we got these 12 depressed individuals, gave them this treatment, and we wanted to see if it significantly improved their quality of life. So in this sense, a higher score means a better quality of life, better quality of life. Uh, so a higher score is better in this case. So we measure them pre-giving them the intervention, immediately post-giving the intervention, and a 6 month follow-up, because often treatment benefits can tail off a little bit. So we not only want to make sure that there's an improvement pre to post, but want to make sure that improvement doesn't peter off too much when it gets to follow-up. So because we've got 3 groups and repeated measures, we need to do a repeated measures ANOVA. Now, this data is probably presented a little bit differently to how you've usually seen it. We usually have a grouping variable identifying whether one participant was assigned to the pre-group and then the next one was assigned to the post-group. But because they're assigned to all the conditions, we've got the variables in columns like this. Now, I did that because that's how you would get the data if you did the analysis in something like SPSS. So that's probably what most people will be familiar with. But that's not how we need to do it. So the order that we're going to do things here is we're going to restructure the data in the format that R needs to be able to do the analysis. We're then going to actually do the analysis and talk about some problems with interpreting it, and then do some follow-up tests, just like we did for the one-way ANOVA, because the one-way repeated measures ANOVA is going to tell us if we get a significant F statistic, that's going to tell us there's differences somewhere between the groups, but then we have to do follow-up, what are called Bonferroni post-hoc tests, to see if where the differences are. So that's the idea. First, what we're going to do is restructure this data. Let's talk about the format we need to restructure it in. The first thing we need to do is add a variable that identifies each subject. So this first one's going to be subject 1, the next one's going to be subject 2, and so on. That's because, unlike other statistical packages, R for repeated measures does the same as it does for independent measures. So for each condition, it creates a separate line. So we need some way to tell these 3 people aren't 3 different participants, even though they're on different lines. They belong to the same person. So let's first add our subject variable. So I'm going to say the name of our data frame, which is DEP, and then the $sign, meaning I want to manipulate a specific column, and I want to add a column in this case. The column I want to add is going to be called subject, and I want to add a vector of numbers, or a column of numbers essentially. So I'm going to use a C function. So wherever I put in here first is going to go next, and participant 1, whatever I put second is going to go next to participant 2, and so on. So I could just list all the numbers down to 12 here. That's probably fine if you got 12 participants, but there's an easier way to do it. I can just use this notation. Putting the colon there means I want to fill in all numbers between. So I want to add a row for all numbers between 1 and 12, because we've got 12 participants. So if we submit that, and now look at our data frame again, we've got this subject variable that we need. So that's good. Before we do anything else, because we're gonna have to restructure the data, but let's just look at some descriptive statistics. So, like we said in the previous video, we need to load up the past ECS package to look at descriptive statistics. So let's go library, past ECS, so that means we want access to everything that's in that package. So we can now use the functions that are available in it. So I'm going to say descriptives. What do I want descriptives for? Well, I want something in my DEP data frame, but what specifically do I want descriptives for? Well, I want descriptives first for the pre-group, and I'll run it again for the post group. And then for the follow-up group. So if we look at our means here, it certainly looks like we start off with a relatively low quality of life, then the mean goes up slightly and then goes down, but only slightly. It goes up between these two time points a lot more than it goes down. So certainly from this, it looks like the intervention has a positive impact on quality of life, and that this doesn't significantly decrease over a long period of time, the follow-up intervention here, but we don't know which of these differences are statistically significant. That's what we need ANOVA for. So, remember, repeat any ANOVA or any statistical test isn't just kind of arbitrarily comparing the groups. I hear people say very often, that there wasn't a significant difference between these groups, or there was. Well, that's not what it's doing. It's testing a particular statistic, or what they call population parameter. So in the case of ANOVA, it's always testing some means or some means on some composite variables. So if we get a significant difference between these groups, it's not telling us the groups are significantly different, just kind of in general. It's telling us that these means are significantly different. So with that said, let's go ahead and do our analysis. The first thing we need to do is restructure this data, and in order to restructure it in the way that we need a package that is affectionately called reshape2. So I'm going to say install.packages reshape2, and I misspelt it, so it may throw an error in a second. I'm going to stop that. Okay, let's rerun the command when it's spelt correctly. If I submit that, we now really should be installing reshape2. Sorry about that error, guys. Okay, so we now have it installed. Like any package, to load up, to get access to the function it provides, we're going to use the library function. So we're going to say we want access to the library that is reshape2. So if we look at our data, like I said, these data aren't in the format we need for the repeat analysis. They're in what's called a wide format, and we need them in the long format. What the wide format means is that every time we test a participant on a variable, it just makes the data frame wider because we just add another column. But in the long format, we add another row every time one participant is tested on a variable. So we're gonna convert the data, and hopefully it'll become more clear. So to make sure I know what it is, I'm just gonna say depression.L standing for wide, and to do that we're going to use melt function because we want to melt these columns together into one variable and make the different columns into different rows in the data set. So I'm going to say melt, and the first thing it's going to ask us is what do you want to melt? Or we want to melt the P data frame. The next thing it needs is what's called an ID variable, and that's how do I know what how do I know what variables pertain to what. That's part of the reason why we needed this subject variable. Fortunately though, if we have only one of the variables that's not one of the things we measured, one of the things we're interested in one of our conditions, this melt function will automatically assume that's what we want to use to identify our subjects. So that's fine. Don't need to worry about that. What we do need to explicitly tell it is what are the dependent variables that you want to make into separate rows, and we do that with this measure dot vars function. So measured variables, I'm going to tell it that our measured variables are called pre, post, and follow up. There's a couple more parameters. That's all we need to write, but there's a couple more parameters we can pass it to make it a bit easier for ourselves to identify. The first one is what do you want to call the variable that identifies our different conditions? So we'll be creating a new variable that tells us whether this row pertains to a pre-measurement, a post-measurement, or a follow-up measurement. So in this case, I'm just gonna we do that with the variable dot name parameter. So I'm just gonna say variable dot name, and I'm gonna call mine time, because that's what our different conditions represent. They represent different times. So we're going to say that, and then the next thing we want to pass it, or we can pass it again, this isn't mandatory, is the name of the value. So it's gonna have our subject name, our variable name, so what condition this goes with, but then it's just gonna have a column called value with the value in it, but we can give that a specific name. So I'm just gonna say value name equals quality of life, because that's what we're measuring. So it'd be helpful to have that identified. Hopefully, if I've done everything right, we'll press return. We should, if we run this new DEP.L object that we created, we should get our data frame, and indeed we do. So this is what long format data is. Each participant has a separate row for each condition. So the conditions aren't in columns, they're in rows. So if you're familiar with SPSS, it's probably quite a strange concept because each participant has multiple rows, which doesn't normally happen, but R knows how to deal with it, and this is the format that we need it in. So with that done, we can now go on and actually run our ANOVA. Now, there are ways to do repeat measures ANOVA with the AOV function I showed you before, or indeed with the linear model function, but they're very complicated, and this is complicated as it is. So we're going to use a function to make it easier, which is ironically called the EZ or EZ, as I would say, ANOVA function. So we need to install that package. So we're just going to say install .packages EZ. If we run that, we see that it's downloaded, and we can now load it up by saying library EZ. We now have access to all those functions. So just like we did in the the other ANOVA videos, we're going to create a model that our overall model of everything we want to test, and then we're going to break it down. So to do that with easy ANOVA, we're going to say model equals the result of the easy ANOVA function, and it's going to ask us for several things. First is easy. It's what data do you want this to apply to? Well, we want to apply to a depression data frame, but the long format one we created. So now I'm going to get a little more complicated. It's going to say, well, what's your DV? Where are all your scores stored? Well, this could get a bit confusing if you're not familiar with this, but remember, we've now got a grouping variable, which you don't normally have in a repeated measure design. So it's not our grouping variable; it's our actual score, which in our case we called quality of life. You see up there, quality of life. So that's our dependent variable. So now I'm going to ask us, what's the within subject ID, or what's the variable that identifies where each subject is? And notice that this is a required field. It doesn't have a default value, so that's why we had to create it for what we've done before. So our variable always stays consistent no matter what the condition is, and identifies just what person that data belongs to is called subject. So next we're going to put in subject. Next we're going to want to specify, okay, you've told me what way your data is stored, but what's the factor that you want to evaluate? What's which factor defines where the different conditions are, or what's the within subject factor. Well, in this case, there's only one remaining variable, which is we created before. It's called time. So we know that that's our within subject factor because we tested the same people at different times. So we're going to say within equals time. There's a couple of interesting things that I'm going to show you just for kind of explanatory purposes. There's one parameter you can pass called detailed, which is by default set to false, but I'm gonna set it to true because I think it's useful. And then because it's a package, the easy ANOVA doesn't use the AOV function used in the past, because with repeat version ANOVA that's quite complicated. But what you can do is get it to return one of those normal models. So that's going to be useful because we can see the mathematics behind how that's actually computed. And I'm not going to go into that into great detail, but we're going to say return AOV, return an AOV object. By default, again, that's set to false, but I'm going to set it to true. And hopefully, if I've done everything right, we should get some output. And it's going to say converting subject to factor, because we didn't do that, but it just as it by default. So that's why I didn't cover it. We can now run our model object. And I forgot there are several different ways you can get summaries of this. Notice it's gonna give us our ANOVA, which is a classic model that we've been dealing with for ages, but it's also going to give us the easy ANOVA output, which is what we're going to look at. I'm going to make this a little wider so we can see what's going on. So what we're interested in here is our variable that we're looking at was time. So we want to see if there's an effective time. So it's going to say what the numerator degrees of freedom are. That's the first degrees of freedom you need to report in an F test, and what the denominator degrees of freedom are. It's going to give us an F value and a significance value. So in this case, that is highly significant. But I did say there's an additional assumption we need to test with repeat and measure ANOVA. And while in independent groups ANOVA, we test that the group error variances are the same, or there's the same amount of error in all our groups. Essentially, we're testing the same group of people in all our conditions in here. So what we want to do is make a comparable assumption and say, okay, we know these groups are going to be related, but in order for us to be able to make any interpretation, they need to be related by the same amount, and that's tested by something called sphericity, and specifically Monchi's test. So for all your within subject factors that have more than 2 levels, you get a Monchi test, and we get a test statistic and a p-value, which we can see is highly significant. So what do you do when you violate Monchi's test? Often there's not a lot you can do when you violate an assumption, but all is not lost when we violated Monchi's test, because there were some simple corrections, what they called, that we can apply. This is going to reduce the degrees of freedom and make it harder for our effects to be significant. So we're gonna use one of those corrections, and it basically estimates how much we violated sphericity and makes a correction accordingly. This first one, GG, is called greenhouse geyser, and that's generally quite conservative. Higher values mean that the conditions are more spherical, or we're closer to meeting the assumption of sphericity, and the greenhouse geyser has given us an estimate of 0.52, and 1 means total sphericity. So it's saying we're quite a lot less spherical than with the another. You get another option out, and that's the Hume-Fell correction, and that's in this case is being a bit nice to it, and it's saying that our data are just slightly more spherical, and then for each one of them we get an adjusted p-value. So because we've violated the assumption of sphericity, we can't use the normal, what's called sphericity assumed p-value that's listed up here. So we have to use one of these corrections. I would normally use greenhouse geyser. Any of them are significant, but I would normally use greenhouse geyser. One thing to be aware of when you're reporting this is that the way this works is it corrects the degrees of freedom, reduces the degrees of freedom, so that when we test it in the F distribution, it's less likely to be significant. And the way it does that is by multiplying the degrees of freedom by the amount of sphericity we have, but it doesn't give you the new degrees of freedom for each value. So when you report this, if you're going to use the greenhouse geyser correction, you need to report the degrees of freedom accordingly. So you need to do it for both. So first, the numerator, or the top part of the equation, has 2 degrees of freedom at the moment. So to know what our greenhouse geyser corrected value is, we need to times that by 0.52. So let's pop open a calculator and say what our current degrees of freedom are. So we've got, in the numerator, for the effective time, we've got 2 degrees of freedom, and we want to times that by the amount that we've violated sphericity. So it says we're 0.52 close to sphericity. So the new degrees of freedom we need to report are, we no longer have 2 degrees of freedom. The numerator, we've got 1.04. So that's what we need to report. And the same for the second or the bottom degrees of freedom. So this is telling us we have 22 degrees of freedom normally. So 22 times 0.52 is going to be equal to 11.44. So those are the new degrees of freedom that we need to report when we're reporting whether our effect is significant or not. So after all that, we've found out that there is indeed a statistically significant effect of time. So, but all that tells us is that there's a difference somewhere between our times. We don't know whether it's between the pre and the post, or the post and the follow-up, or between all of them. So we need some post-hoc tests to look at that. Now, in some of the last videos we've done Tukey post-hoc tests. Now, they're great for independent groups designed to control that error rate, but also give us what we need to detect a significant effect. You can't use Tukey in repeated measure analysis, because one of the things that assumed is that our scores are independent, and obviously, as they come from the same people, then they're not independent. So we need an alternative, and for that we need to use something called Bonferroni post-hoc test. This basically just uses a load of t-tests with a pooled error rate, and but if we do loads of t-tests and use the 0.05 significance criterion, we're going to be having a lot more chance of rejecting a false or rejecting a true null hypothesis and committing a type 1 error. So what the Bonferroni test essentially does is it does a t-test, but then times our p-values by the amount of tests we've done. So it basically makes it so that for each test, if we reject the null hypothesis at the 0.05 level, it means that we've still only got a 0.05 chance of making an error altogether, and not just on an individual test. So that's what we're going to use. To do that, we're going to use, because we want to do a test for each of our groups, compare it to the other groups, so we can look at any differences we want to look at. So to do that, we're going to use the pairwise .t-test function. Now, much like the t-test function itself, even though we have all our data organized into a data frame up here, the t-test function can't use that. It needs the scores as a separate variable, and the groups it wants to be comparing as a separate variable. So the way we're going to do that is just to pull out individual groups out. So first, it's going to ask us, what's your dependent variable, or what do you want me to compare the groups based on? So we're going to say it is something in our DEP long format data frame, but what it is, that's what we're using this $sign for again. What we want you to measure, the variable that we created is called quality of life. So the next thing it's going to ask us for is what groups do, or how does it know what different tests it wants to do? What groups are we comparing? So, well, our different groups are contained. If we go back a bit, our different groups are contained within this time variable. So, using the same notation, we're going to say dp dot l time that would do a t-test and compare each of our different groups, but we need to add in a couple of extra things. For one thing, we need to add in that type 1 error protection we talked about. So we're going to say p.adjust method, I'm going to say equals on Ferroni. The last and actually one of the most important things you need to specify, because this is repeat and raises, is that the data are paired, because if we just said just run this test, it would do it as an independent groups analysis. So it would assume that there's variability between participants, so we wouldn't be getting the statistical benefit of there being less individual differences. So it would be harder for it to be significant. So because it is paired, we're going to say paired equals true. And if we run that, we see our values. So because this is less than 0.05, we know the difference in the means, remember, because we're comparing means, we're not just arbitrarily comparing the groups. Like I said before, the difference between the means is significant. P equals 0.01. There's also a significant difference between the pre and the follow-up group. It's slightly less significant. They're slightly closer at follow-up to their pre-score, but it's not too bad. But then if we look at the post on the follow-up, there's no significant difference. So in other words, they don't get significantly worse again between the pre and the follow-up. So that was just an example of how to do repeated measures analysis of variance in a one-way analysis. You can do factorial analyses in much the same way, like I explained in the factorial independent ANOVA video. So, and it's just following the same procedure. That was a very long video for a very simple analysis, but I wanted to explain the assumption of sphericity and the kind of the logic behind repeated measures designs, and there was also a lot more we had to do with restructuring the data from wide format into long format. So we've covered a lot in that video, a lot of just kind of generic R skills too that will be useful in lots of analyses. So with that, I hope you've enjoyed this video. Subscribe if you liked it, and thanks for watching. Bye bye.